This video is brought to you by Hygromo Chalk. Use code TPSA 10% off to get a discount. Great. So now we can get on to the topic of cardinality. So we say that two sets, completely abstract, A and B, have the same cardinality if there exists a bijection between them. And we write these straight lines around them to show their cardinality, and here they're equal. So for example, here the cardinality of 0, 1, 2 is the same as the cardinality of 4, 5, 6. And we can find an explicit bijection if you'd like, where you just add 4 to every number to get from here to here, and the inverse just take away 4. And here we have two sets without the same cardinality. 1, 2 does not have the same cardinality as just set 1, because if we were to try to find any map from here to here, well, there's only one choice. Both of these numbers have to go to 1 if we want to try to find something bijective, because we want it to be surjective. So we have to have this covered, but this wouldn't be injective. So no such bijection exists. So for these finite cases, this is sort of your normal idea of cardinality. These would have cardinality 3, cardinality 2, cardinality 1. And we say that any set A is finite if its cardinality is the same as some list from 1 to n for some natural number n. And here we would say that A would have cardinality n. Otherwise, A is infinite. Now there's two kinds of infinity that we'll deal with, which is countably infinite and uncountably infinite. So A is countably infinite if it has the same cardinality as the natural numbers, and uncountably infinite if it doesn't. And A will be countable if it's finite, because we can just count the sets in a finite amount of time, or if it's countably infinite, and we say it's countably infinite, because if we had an infinite amount of time, there is some way to at least count all the natural numbers. It's a very easy way to start. You just go 1, 2, 3, and if you had an infinite amount of time, you would count them all. But for uncountably infinite sets, no matter how much time, if you had an infinite amount of time, you still wouldn't get them all. So an example of an uncountable set is given by, you may have seen this before, it may be in a computer science course, Cantor's diagonal argument, which says that the unit interval 0 to 1 is uncountably infinite. So within here, there contains uncountably infinite, uncountable amount of real numbers. And from this, you can very easily conclude that the entirety of the real line is uncountable. So let's suppose that it was countable. So there would be a bijection from f from the natural numbers to 0, 1, and we can write out all of its values. So at 1, 2, 3, on forever. And we'll write them out like so: 0 point, and then a certain string of digits. So all of these are just some digit between 0 and 9. And of course, every number in here is of this form. So if this bijection existed, this would be how they all look. So I've numbered them. The first digit of each one would be, its second index would be 1, and its second index, the next one would be 2, 3, 4, and then the primary index is just keeping track of which little row we're on, or which number we came from in the bijection. So we can define a new number here. I'm claiming that we're going to make it so that it's not on this list. So it's going to be 0 point b11, b22, b33, b44, where bnn is given by 0 if ann is not 0, and 1 if ann is 0. So essentially what we're taking is the digits here are just going along the diagonal. This is why it's called the diagonal argument, the diagonal of all these numbers. And we look at it and say, is it 0? If not, well then great, we'll take this digit to be 0. And if it is 0, well then great, we'll take it to be 1. And from that, we can very easily conclude that bnn is not the same as ann for any of the numbers on the diagonal. So basically, you go along the diagonal, and we can essentially you construct a number which is going to differ here in the first. So it differs from f1 for sure in the first digit, because we've just flipped it either from a 0 or 1. So it means that this number here is different from f1 in the first digit, which means that it's different from the entirety of this. It's different from f2 2 and the second digit, which means that it's different from the entirety of this. Different from f3 3, so f3 in the third digit, so that means it's different from the whole number, and so on and so forth. So just from this rule, we can conclude that this number is not in this list. So that means that we've missed one. This map wasn't surjective. There was some number here that we didn't get in our bijection. And no, I haven't actually said anything about this function other than the bijection. So no matter how general it could be or how much you play around with it, you'd always miss this number here, because we've constructed it to be unique. So that means that this is not a bijection. No such bijection can exist. Therefore, this interval here is uncountably infinite. So we have a theorem here that states that every subset of n is countable. This should be obvious if the subset is finite. If it is not finite, well, it'll still have a minimum element. So you just basically write all the elements in order, lowest, and then going upwards, and then just assign 1 to the lowest one, 2 to the next highest one, and so on. Here we have a statement that says that if A is not empty, that it is equivalent for A to be countable if there is a surjection from n to A, which is equivalent to there being an injection from A to n. And this is an easier way to check countability, but these two statements should seem equivalent to being countable, because we'd want there to be a surjection from n to A, because if we have elements in A that we've missed, like with the Cantor's diagonal argument, then it wouldn't be countable. So we want that n will be able to write f of 1, f of 2, f of 3 all the way down and not miss anything. We want this injection case to hold, because we want to be able to label every element in A with some natural number and not have any repeats. So not have any two elements in A sharing the same label. That wouldn't be injective, but you can see that wouldn't allow for a bijection in the regular countability definition. So using this, we can prove much more easily that Z is countable, because we only have to worry about finding a surjection from n to Z. Well, we'll just do f of n equals n over 2 for n is even. So you should see, if you fill in n to be 2, 4, 6, 8, that will map to 1, 2, 3, 4, so we'll eventually get all of the positive integers, and minus n minus 1 over 2. If you fill in n is for n being odd, so you fill in n to be 1, 3, 5, that will map to 0, minus 1, minus 2. And you'll see how we'll be able to fill in all of the sort of left-hand side of the integers. And it doesn't really matter if you like in your head that sort of we're getting through the natural numbers twice as fast as we were the integers. We don't have to worry about that with cardinality. You can just see how no matter what integer we're trying to find, we can find, if it's negative, we just find some n, some odd n that works, and if it's positive, we find some even n that works. So essentially, if our answer was, 13, then the n here that would work would be 26. And that shows that it would be surjective. We can also show that this product here of the natural numbers by itself is countable by finding just an injection from n by n to n. You can see how you'd kind of do it visually here. you could start at this one and then kind of zigzag around, and you can see how you kind of get a pattern going where you would cover the entire grid of n by n. Or you can show it directly by taking, this is a very common example, xy goes to 2x to 3y, and suppose that for some xy, a, b, pairs of natural numbers, this holds true, so that f of x, y equals f of ab. Well, if x is greater than a, then we bring 2a to the other side, and we have 2 to a natural number, which is going to be even. 3 to a natural number is going to be odd. Even by odd should be even, but here we have that it's odd. Contradiction. So then x cannot be greater than a. And then if it's less than a, we have the same issue. Contradiction. So it means that x is equal to a. And we do the same idea with y and b. So y should be equal to b. Therefore, x equals a, y equals b. It was an injection. So that's from this part of the theorem, n by n is countable. And in fact, the product of any two countable sets is countable, which the idea follows from this. We also have a theorem that states that the union, the countable union of countable sets is countable. And by countable union, I mean that it's been indexed by the natural numbers. So you might recall we previously had sets that were indexed by every point in some subset of R, D, which would not be countable, because RD is obviously not countable because R is not countable. So just to prove this briefly, we can, because each AI is countable, then there exists an injection from here, from AI to N. We call that Fi, and F will take the entire union to this direct product here, which we also know to be countable. So it'll send x to fkx comma k, where k is just the smallest I, such that x is contained within that some ai. So we say that f is injective because if this equality held, well, obviously k and j are the same. And because k and j are the same, how we defined what this second number should be, it should be the smallest natural numbers such that x is contained within ai. That means that x and y both contained within ak, which is the same as aj. Well, because this is true, that means that f of k of x equals fk of y, and we know that fk is injective, so it means that x equals y. So that means that f is injective, so we have an injection from this union to this product, and this product we also have an injection to here. So that therefore this union is countable. And from this we can prove that the rationals are countable, because the rationals can be written in this form here. So it's this union from n goes from 1 to infinity of m divided by n, where m is an integer. So you can see that all rationals will just clearly have this form. And because we're saying that n cannot be 0, there's no issues here. And we'll just say that briefly that each one of these is countable as it would be in the theorem, because, well, we can very clearly go from m over n for any fixed n to m, which is an integer, and we can go from integers to the natural numbers. The integers are also countable. And then finally, a theorem to say that if the cardinality of A is less than B and the cardinality of B is less than A, well then their cardinalities must be equal, which this should make a lot of intuitive sense.